Hey everybody, welcome to our flip lesson on similar figures. Now we have just studied dilations, and dilations are a precursor to understanding similar figures. So first of all, I guess what we ought to do is we ought to define what it means for two shapes, two objects to be considered similar. And that definition is that these objects have the same shape, but not necessarily the same size. Now they could be the same size, but they don't have to be the same size. As long as their shapes are the same, then they're considered to be similar. And if we go for a more precise explanation of similar polygons, then we know that similar polygons have equal corresponding angles and proportional corresponding sides. The angles have to be equal. That maintains the shape, but the sides can be bigger or smaller or the same. That proportional sides controls the size of the polygon. So the equal angles, that gives us the same shape. The proportional sides controls the size. So let's jump in and let's take a look at some similar shapes. So right here, this dog, that is my original shape. Which shapes over here to the left would you consider to be similar shapes? Well, again, that idea of similar means same size, means same shape, not necessarily the same size. You'll notice this dog way too skinny. Even though the height is the same as this dog, the width is not. This dog has the same proportions. It's not too skinny, nor is it too fat. So the similar dogs would be these two. And you'll notice this dog here that I just circled, it happens to be identical to that dog, but similarity doesn't mean it has to be bigger or smaller. It could be the same size. What we care about is same shape. And down here with these rectangles, yes, these are rectangles. They have 4 right angles. But with similarity, we need the angles to be the same, and all 4 of these have the same angles, but we want corresponding sides to be proportional. And that's what we have with this rectangle and the original one there. So similarity, we need same shape, not necessarily same size. And when we're talking about polygons, we could be more specific. Corresponding angles need to be the exact same. So angle 1 here has to have the same measurement as angle 1. Angle 2 here has to be the same as angle 2, but the sides, those can be proportional. They can be in like a 5-to-1 ratio. So let's get on and take a look at some of these problems in our guided notes. Suppose we wanted to enlarge or shrink the following shapes with the following scale factors. Now that scale factor, those are the proportions we use to find the size of the sides. So here the scale factor is 3. And what that means is I'm going to take this 3 and I'm going to multiply it by each side. So if this original side right here is 6, when I multiply it by 3, it becomes 18. And we're going to do that with the corresponding sides. This side is 4, so this side right here, the side that corresponds to that 4, using this scale factor, would be 12. And finally, this side, which is 3, the corresponding side, which is this side, using this scale factor of 3, would be 9. And that's what a scale factor does. A scale factor tells you how much you enlarge or reduce each and every side going from one shape to the other. So if we went back to these dogs, the scale factor going from this dog, the original dog, to this dog right here, that would have a scale factor of 1 because it didn't change size at all. But going from this dog to that dog, it looks like the scale factor might be 1/3 because this dog seems to be 1/3 the height and 1/3 the width of the original dog. Again, I'm just guessing there. So when we come over to part B, the scale factor is 1/2. And since that scale factor is less than 1, it's going to shrink it down. So again, these are polygons, so we look at the side that corresponds to this, which seems to be this side, and we use that scale factor of 1/2, and that gives us a 3 here. It gives us a 2 here, a 3 here, and a 2 here. Scale factor, this idea of a scale factor, that's what controls the size of the object. Now, let's talk about proportional sides. So we have one triangle on the left, or on the right, with lengths 6, 7, and 8. And we have a triangle on the right with sides 3, 4, and 5. And my question is, are these triangles similar to each other? Well, if they are similar, then the sides need to be proportional. We have to look at the proportions involved for each of these sides. So let's set up a proportion. Let's compare the smallest side of the red triangle, which is 3, to the smallest side of the blue triangle, which is 6. And what I want to do is I want to see if that's equal to the ratio of the two, let's say, largest sides. So the largest side here is 5, and the largest side here is 8. And if these shapes are indeed similar, then their sides have to be in the same ratio. That's what it means to be proportional. Well, I don't think this quite works out, because 3 over 6 is really 1/2. And 5 over 8, that is not 1/2. It doesn't reduce. As a matter of fact, it's bigger than 1/2, isn't it? So since these are not equal, I'll put a slash through it, then are these triangles similar? No, because their sides don't have the same proportion. Small to small is not the same as large to large. And if they were similar, they would have to be in that same ratio. They would have to be proportional. Now, moving on, we have this situation, and there's a little bit of reading involved, so I'm going to let you do some of that reading. So pause the video and read part A. Welcome back from pausing the video. The question is, Colby has compared the height of this letter C to the height of this letter C, and he set up the ratio 24 over 8. And then he compared the width of the big letter C to the width of the little letter c. And he's claiming that these are indeed equal. He's claiming that this is a fair proportion to set up. Are they equal? Well, there's a couple ways we can check. There really are two ways you can check to see if you're dealing with a true proportion, if your two fractions are equal. One is you can reduce each side. So over here, I know that 8 goes into 8 one time, and I know 8 goes into 24 3 times. So this fraction on the left reduces to 3 over 1. On the right, I know that 6 goes into 6 one time, and I know 6 goes into 18 3 times, and so the fraction on the right is also 3 over 1. And if those are equal, then yes, it is a proportion. I'll make a little smiley face. Now, you can also see if something is a proportion by cross-multiplying. Anytime you have a single fraction equal to a single fraction, you can cross-multiply. And so what I could do over here is I could do 24 times 6, and that turns out to be 144. And then you can cross-multiply 8 times 18, and again, you have a calculator. That also is 144. And as long as those are equal, then yes, you do have a proportion. So in this particular problem, the ratio that Colby set up, it is proportional. Now, what Colby did is absolutely right. These ratios are equal, and they're good ratios. I mean, what he's comparing is the height of, the height of the big to the height of the small, the width of the big to the width of the small. And those are very consistent ratios. But then we get down to part B, where we have Sam, who set up a different ratio. Sam set up the ratio, whoops, I don't know what happened there. Sam set up the ratio of 8 over 6 compared to 24 over 18. So what is he comparing? Well, by comparing 8 to 6, he is comparing this height of the small shape to this width of the small shape. And he's comparing the height of the big shape to the width of the big shape. Now, does that work? Well, sure it works. These are very consistent ratios. We're going height on top, width on bottom. Height on top, width on bottom. And if we cross multiply, we get here 144, and we get here 144. And yes, those are equal. So yes, that's a very fair proportion to set up. And finally, we have Chloe, who has decided she's going to make a letter C, and so she needs to find X. And so what's Chloe going to do? Well, she has two options. One is she can compare height to width of the small one, and that has to equal height to width of the big one. And she can solve for X by cross multiplying. 8X equals 120. And when she divides by X on both sides, she gets X is 15. Or Chloe could have set up a totally different proportion. She could have compared 8, which is the height of the small, to 20, which is the height of the big. And if she did that, then the other side, again, she's going small on top, big on bottom, would have to be 6 on top, X on bottom. And you'll notice when she cross multiplies this, she gets 8X equals 120. I mean, she gets the same thing. She gets X equals 15. And so as long as your proportions are consistent and make sense, then yes, you can set them up. And there are lots of different ways you can do these problems. Let's take a look at one more problem set together. And we're told that these two five-sided figures, these two pentagons, are similar. And Elena set up this proportion. She is comparing 6, which is this piece, to 4, which is the corresponding piece. So big top piece to big top piece over here. And in the bottom, on the right side, she compares 8 to X. And the question is that correct? And the answer is yes, she is being consistent. She is comparing the left-hand part on top in both cases, the right-hand part on the bottom in both cases, and she's matching up the corresponding parts. And if we cross multiply this just to play around, we get 6X equals 32, and you can solve that for X by dividing by 6, and we get a fraction, which is okay. I think we get 5 1/3. Now, what about the next person, Roderick? Well, Roderick set this one up, so let me erase this and let's see what Roderick has done. Roderick set up a different proportion. He is comparing 6 to X, and then he compares 8 to 4. Is that a valid proportion? And the answer here, no, it is not, because he is not comparing corresponding things. 6 does not correspond to X. They have absolutely nothing in common. This is not a valid proportion to set up. And if you tried to solve it, you would get 8X equals 24. You get X equals 3, and that is not the value for X. X does not equal 3. That is a sad face. I mean, how could X be 3? 6 is smaller than 8. 4 has to be smaller than X. That does not work. But let's take a look at one last case here. I'm going to let you do this for homework.